Hello, there they are. Aneth, good afternoon. Wow, that was a double. All right. Yes, good afternoon, Michelle. F. Good afternoon, Paulina. H. Good afternoon, Stephanie. I. There's no I in team, but there is a me backwards. Okay. Good afternoon, Cheska. That was a polite laugh. Thank you. Okay. Good after Cheska P. Good afternoon, Yavi B. Good afternoon, B. All you can be. All right, I'm gonna stop. Good afternoon, Chris R. And now to the chat, and but I really appreciate it. Good afternoon, Marilyn, whose last name I'll remember in a second. Good afternoon, Michelle in the chat. Good afternoon, Fariel in the chat. Good afternoon, Freddie in the chat. Good afternoon. Okay, Michelle Q. Oh, Michelle Q is like the under radar. She like sneaks in these. You never know. Anyway, okay. Good afternoon. Emily is here. Emily, who? All right, I'll keep my thoughts to myself. But thank you, Emily, for making it. I totally get it. Yeah. Okay, I see you, so to speak. Good afternoon, Shy. Good afternoon, D. Good afternoon, Brooke L. Good afternoon, Paulina H. Good afternoon, Marilyn. I'm gonna have to. All right. Anyway, I don't know why I'm blocking on Marilyn's last name. Don't tell me. I'll figure it out. Good afternoon, Katie M. Good afternoon, Allison M. Good afternoon, Yavi B. Hey, okay. If I can't take the heat, I'll get out of the kitchen. Chris and Harry. Wait, right. Yes, Fariel. Right. I know. I actually have that in my mind, but I still bump on it for some reason. I don't know. And it's weird because my son is literally right now in his school's doing a production of Little Mermaids. Anyway, whatever. Good afternoon, Harrison. Okay. Are you in front of my office? Well, do you get extra points for loitering? I mean, oh, you really are. Okay. Well, that is a good location. Yeah, you get extra points. Okay. As long as you don't defit. If you loiter without doing graffiti, then yes. If you can slip like a coffee under the door, even better. Just kidding. Okay. Yeah, please don't. Okay, yes, you get extra. Chris doesn't even need extra points. He's got like infinite. But what did I say that? All right. What is he? Well, today Felix is at school camp. He's at anyway. Um, he's at school. Yes, I said right. Okay. He plays a lot of. All right, I'm gonna stop. Okay. So we should start. We should do physics, but there's one thing. Wait. We're going to do physics. We are really going to do physics right now. I'm blocking on one. Oh, Maryland's not. Yes, Maryland C. That's right. Sorry. Chocho. I will never get. How could I have not forgotten that? I will never get that wrong again, except I totally will. Chocho Fariel. Chocho. It is pronounced. Tell me if I'm pronouncing it right. I don't think I've ever said your last name, Maryland. Sorry about that. Okay. All right. We're going to do physics. We actually have a lot of physics to do. It's because, oh my God, you guys, wow. No, I didn't say odd. Did I say no? It's unusually beautiful, just like Yaverbaum. It is unusual. I just like that it's a double. I'm gonna stop when you're too far down the hole. Stop digging, Yaverbaum. But no, I like your last name. Okay. Um, um, okay. Physics. Yes. What we have to get to now is question 9 of homework 1B. Finally, like, yeah, for those of you who are still having faith that would ever happen, it's going to happen now. So question 9 is big. It is the point of all of homework 1B. It is not an easy question. Okay. It's not meant to be it's not something people could just like, in order to make any kind of headway with question 9, one would have had to have thought somewhat patiently and hard. Like, you can't just get it in 3 lines. And one might have even have done Google research or something like that, which is fine if you do it right. It's certainly not cheating when it comes to homework, right? And then one also might have like paid attention in labs and gotten more and more insight into question 9. But just as we embark in it right now, do I think for a minute that anybody could just like get it the night that I assigned it just because I assigned it? No, it's right. It's meant to motivate a lot of thought. And the idea is that by the time we get to going over question 9 now, I know that you've already seen things on the web. You've seen things in the lab. I know that people have seen a lot of pieces that would hopefully have help them see some aspects of what's going on in question 9. But the idea still is that they're hard enough pieces, and there's enough of them, that when we discuss it now, when I start lecturing on it now, hopefully at least I'm like addressing curiosities or confusions or questions that have been in your mind because you've seen these pieces now, rather than just like talking into outer space, like I sometimes do, right? Like, so the idea is I know you've thought about it in many ways already. But hopefully that means that now what I say will will be the glue between the pieces that you've seen. And again, also for people who've never had me before, that's why you still could get all 35 points on this homework if you wanted to, because it's not expected that you could just like nail it on the first night. But it is expected that if you go through drafts and revisions and think about things and put together the material from the lecture, blah, 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 then you eventually do understand it and then could eventually have an exam on it, which eventually will happen. So wait, so I will be there. Okay, I'm looking at that. So, okay, so question. So just know it's all part of the, that we're not off, that nothing's gone wrong in the class for you or for me yet. So here we go. So homework 1B, question 9. So I'm going to try to do this thoroughly. I'm going to do this one with the 5-step method because, I think it warrants it. So very quickly, let's just give the diagram really quickly. Oh, and again, also, I know I'm being all defensive and used car salesman-y. Like, but so question 9 is hard, right? That's what I'm saying. It's hard. Like, it's not easy. It's hard, but it's also super important. So that at the end of the day, what we take away from the answers to question 9, the equations and the solutions to the equations that we take away from question 9 end up sort of governing the majority of the rest of this class. Like, certainly, like many weeks to come. Okay, so I mean that's why I think it's worth it. Like we're going to land at a mathematical place from this that we build everything in the rest of the course on. I mean, not to make too dramatic a point, but this is not all just about a particular mass on a particular spring. It's about what we ultimately call simple harmonic oscillation in general, which then also forms the foundation of, say, the course known as PChem. Like a lot of PChem rests on understanding like this thing that we're about to do. So that's why we make a big deal of it. So okay. So okay, so that's our diagram, right? Okay. And we know that X naught happens to be 0.5 meters. And we know K happens to be 200 newtons per meter, and we know that M happens to be 3. But all these are these happen to be the numbers. Ultimately, the numbers are not the issue here. So this is all my step 1, right? This is my diagram and fact pattern. Okay. So then step 2, as you know, the question of question 9, the question is, at t equals 1 second, what is X, right? That is the question that we're being asked. Again, note, it's a simple question. I'm not saying it's an easy question, but it's a simple question. It's just like, I name the time, can you name the space? In fact, it's all physics always comes down to this. I name the time, can you name where the thing is going to be? In a way, it's almost surprising that this wasn't the first question of the sheet, right? It almost seems like it should just be like the straightforward request right now. So I'm going to try to solve it now, but there's a reason it's not a straightforward. It's straightforward to ask. It's not straightforward to answer. Now, why? So first thing I want to say as I move to step 3 here, I'm saying where's the mass going to be at 1 second? I don't really care about 1 second, right? That's just an example to make this concrete to picture. Really, what I need what the question's really asking for is position as a function of time, right? Like if I had some equation or some formula, X equals blah, 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 T, which I wish I had, then I would just plug in 1 for T and it would spit out the X, right? If I had such an equation, then this would be a joke of a problem. But I don't, as it turns out. What I'm really looking for is to derive once and for all some equation. I'm looking to derive an equation that expresses position as a function of time for this situation, right? So, and when I get that equation, I'm basically done. Then when I finally get that equation, I will plug in 1 for t and it'll spit out x. And I'll realize I never really cared about the 1. That was just an example. The real issue is what is x as a function of t for this oscillator, right? If for this situation, this mass that's going back and forth, oscillating, this cyclical motion. That's what I'm looking for, right? So that's all the work I'm going to do for the rest of this period is going to be to do the math or the physics required to get an equation, a function, x as a function of t. I'm going to say one more last time and then I'm going to move on. Note, once upon a time, we might have thought that the point of physics is like you solve problems by using equations, that you use equations to solve problems. It really turns out the deeper and deeper you go into physics, or the more and more that you're actually doing physics rather than just using physics, it turns out that our goal, especially in the lab, is not to use equations and plug into them, but to discover them, to derive them. They came from somewhere, right? Somebody who was originally doing physics didn't have a textbook full of equations. They had to figure them out. So they are figure outable. So that's what we have to do here, right? And there's different equations for different situations. So I'm going to start step 3 now. But step 3 is going to be a little involved today. Step 3, general definitions and principles. I'm going to write some down, but really, I have to caution here's where I'm going to do some real work here, because we're going to have to figure out a principle or some kind of equation to use here. So let me start by saying this. Like, I'm going to pretend like that this is you doing your homework or you taking an exam. If I need x as a function of t, maybe I should do this in a different color, but I'm looking for x as a function of t. So I would not be crazy if I thought, well, I've got, if I started looking up on the web or in my old notes from an old physics class, do I have any equations that relate x to t? And of course we do. And in fact, we spent most of physics 203 using them or coming up with them. One classic equation that we definitely used a lot in physics 203 is this one: x equals 1 f at squared plus v naught t. Now I'm not saying that I should be writing this. I don't know. I'm writing this down. I'm not crossing it out. I'm highlighting it. I'm writing this down because it's true. X equals 1 f at squared plus v naught t is true. And it is an example of an xt function. It gives me an example of the kind of thing I'm looking for. And if you wrote it down in your homework or on an exam, I would give you points for this because it is true and because you're moving forward in solving the problem. But one of the advantages of that, and you're not stuck, you're not stopped, you're writing something down. That is true. It is true. But once you write it down, one of the purposes in writing it down might be that you might notice then that it's not good enough. We haven't really cracked the code yet, because you would notice if you look at it, the thing that we spent time on this homework on questions 1, 2, and 3, we realized here A is not constant. Acceleration is not a constant in this situation. That equation we used to use in physics 203 assumes that there's a value of A that you can just plug in. But we found in this situation that at x equals 0.15 meters, A equals negative 100 meters per second squared. And then at x equals 0, A equals 0. So A is changing, right? So it doesn't mean that equation's wrong. It means it won't help. It doesn't apply here. So I need more, right? But I want to emphasize again, like I'm trying to teach you the right answer, of course, but what I'm really trying to teach you is like what to do when you don't know the right answer, right? Like, so I want to encourage you again, like if this were an exam right now, if this were homework, you would it would be helpful and productive to write down things that you think are true. And then you can look at them and be like, okay, but I still have to go forward. You would get points. You would not get points off for what I just did. And in fact, if you literally did what I just did, if you wrote that equation down and then wrote, but the problem is A is not constant, so we need more, I would be so impressed and happy. Like the thought process is right. Okay, anyway, so I'm going on. So the next page. Well, so I'm still on step 3. This is still step 3, a little more tricky. So what does apply here? Well, first of all, F equals ma still applies. It always applies. It was applying in the first 3 questions, right? Like some of the forces does equal mass times acceleration, but also what applies here specifically is we have a spring. Like these 2 GDPs we used in the first 3 questions, they're still true. Hold on, I'm just changing the, hold on. I will be, okay, hold on, I'm still here. Okay. So there's no other forces acting or doing work, right? Therefore, if the only force acting is the spring force, and if the sum of all the forces equals ma, then here in this situation, sorry. Well, not sorry. There's one other thing I want to say. Do I want to put it right now? Yes. So F equals ma, F equals negative kx. And before I put those things together and move to step 4, let me also say, okay, the issue here, why we can't use old physics equations, why we have to develop a new equation here, the issue is that the acceleration is changing, right? That's what I'm saying. Like to pick up from yesterday's class, like the issue is that this thing is moving, so it has velocity, but the velocity is changing, so it has acceleration. But the acceleration is also changing, it has jerk. And in fact, if you really start thinking about it, the jerk is changing as well. It has what we call whip, etc. Every derivative is happening here. So that's what makes this intimidating and hard. Not impossible, just new, right? So if the acceleration is changing and we can't use our old constant acceleration equations, like pro tip or like problem solving strategy, if acceleration is the issue, if acceleration is what's in our way, the fact that acceleration is not constant, what that means is I shouldn't run away from acceleration. It means, as from a problem solving standpoint, I should lean in, so to speak, and really confront the acceleration itself in a way that maybe I haven't in the past when I didn't have to when it was a constant. In other words, what am I saying? I'm saying acceleration is changing here. Acceleration by definition is change. Acceleration is the derivative of velocity with respect to time, and velocity is the derivative of position. So that's something we do know about acceleration and is always true. I'll say it one last time. What isn't true about acceleration here is that it's constant. We can't use that anymore. But what still is true is that the definition of acceleration is derivative of velocity with respect to time, which means second derivative of position with respect to time, right? That is a GDP. I can rely on that. Acceleration is, by definition, the second derivative of position with respect to time. Now, so those are my 3 GDPs that I'm going to use. Again, if you never did this before, like it's one thing for me to give you a fish, right? But if I'm trying to teach you, and the expect give a person a fish and they can eat for a day, teach a person a fish and they can eat for a lifetime. It's like true, right? So because there's always this thing in physics, like, yeah, he gave me the answer, but like I don't know what to do. And I'm like, well, what I'm saying is, how did I know to make these 3 things my GDP? The first two are my GDP because that's what I've been using through the whole problem. Like they're true. It's a spring exerting forces. But then this third one, why I'm suddenly introducing it now, if it seems out of nowhere to you, is because the issue is acceleration. So I'm writing down something that is still true about acceleration. That's like, okay, anyway. So I'm going to go to step 4 now. I'm going to put these things together and start making progress on this problem. Step 4, PAW. So in other words, here then, according to what I just said above, negative kx equals ma, right? I'm just putting together the equations I just wrote above. So negative kx equals ma, as we said in question 1 and 2. Therefore, negative kx equals m dx dt squared, right? Now, I'm even going to go one more step. Hello. Well, yeah, okay. So before I go to the next step. So now look, I'm now making progress. And in fact, this is maybe another argument for why did I suddenly pull in a calculus definition of acceleration? Well, partly the reason I already said, but also partly because look, now that I've made these substitutions, I'm not done. I'm not done. But but I'm making progress because let's keep our eye on the prize. What we're looking for is x as a function of t, right? What that really means is we're looking for an expression. We're looking to derive a new equation or new function which treats t and x's as the only variables in the equation, right? We're looking for a function such that t is the input variable and x is the output variable, and anything else in the function is some kind of constant number. Even if it's written as a letter, everything else is supposed to be, I mean, whether we know the number or not, everything else has to be a held still constant number. In other words, we're seeking an expression for which t is the independent variable and x is the dependent variable, right? That's what we're looking for. So the fact is, one of the other reasons I substituted d2x over dt squared for a is I'm getting there, it seems, because now I have an equation now. I'm not done, but oh my God, sorry. I'm not done, but I have an equation for which there's only two variables in it, x and t. And in fact, the two variables are being treated exactly the way they should. Like you can tell that since t is in the denominator of some derivative expression, t is being treated as the independent variable. And x is in the numerator, so it's being treated as the dependent. And this x is the same. Hello, sorry. And this x is the same x. And everything else in that equation, don't be fooled, is not a variable. Everything else, the k, the m, they are just constants. They might as well just be numbers. In fact, in this example, they are numbers. So it's like 200 newtons per meter and 0.3 kilograms. But, right? So we've arrived at an expression that is the correct information that we're looking for. It's treating x as the output and it's treating t as the input. It's the correct information, but it's hello. Sorry, I don't know what just happened. Oh my God, please tell me we're still. Sorry, I don't know why that's happening. Hold on. No. Okay, yeah. Everybody panic. It's a correct information, but the form is wrong. It's not a direct form. I mean, right now, as it stands, I don't know what it would mean to plug in. I want something where I can just plug in 1 second for t and it'll spit out an answer for x. That is not what I have here. So I've got to do more work, but I've got the right information, just the wrong package. So the first thing I'm going to do is the same thing I did a second ago. A second ago, I said, oh, acceleration's the issue. Darn it. So then I had the courage, the intellectual courage, to dive into the acceleration and write down a statement that was true about acceleration. Same thing here now. I'm looking at this and it's like, it's getting there, but it's like a little annoying because like instead of just having x and t, it has a derivative of x and t in it. If you're slightly intimidated or annoyed by that, you're not alone, right? Like I don't want a derivative there any more than you do. I want x. So what do I do? That takes getting used to in physics and math. What we do is we lean into the thing that's intimidating us. Like honestly, like it's not just because in other words, if what I have there is a derivative and that's not really what I'm looking for, I'm looking for the original function. Let me focus on trying to unpack that derivative. So the first thing I'm going to do is clean this up a little bit. I'm going to focus on I'm going to isolate the derivative. Pause for a second. Sorry, 1 second. Well, you'll see that. So I'm just doing algebra right now. It's not a big deal, but I'm just going like this. Okay, so I just isolated the derivative. That's all. Give me a second. I just using it on the computer. Okay. Okay. Okay, so I've just done that. Okay. Now, this thing, we're still not done, but let's pause for a second. I know again, I'm sure you've seen this on the web if you tried to get any help with this homework. And I think you saw it in lab or some version of it in lab recently. Let's talk about it for a second. This thing is an equation that has a derivative in it. That's not a joke. And it's an equation that has a derivative in it, but okay. It's an equation that has a derivative in it. But again, like I'm saying before, it's not an equation that's going to solve something for us because it has a derivative in it. It's not going to solve something for us. We need to solve it in order to complete this problem. So it is an equation with a derivative in it, but it's a very specific type of equation that has a derivative in it. As you may know, this thing is called a differential equation. Okay. This thing is called a differential equation for a very specific reason, not just because it's an equation with a derivative in it, for a reason that's deeper than that. I'll explain in a second. But before I even explain anything, this is like always one of my favorite moments in the class. Let me just be very clear. This is a differential equation. We need to solve it. There will be a couple more in this class that we will need to solve. And then we'll need to use those solutions for the rest of physics. And we're going to use those solutions to these differential equations in PChem. I mean, those of you who are taking PChem, which I think is most of you. Let's be clear. You were not required to take a class. Well, no, let me back up. Differential equations are a big deal. They're not a joke. They're like real. And there's entire math classes devoted to them called differential equations. There's not just one, there's many, just like there's Calc 1, Calc 2. Okay. You could spend your life taking courses that teach different techniques and tools for how to solve different differential equations. No, I don't expect any of you to have done that. You were not required to take a course called differential equations before taking this class. It is definitively not a prerequisite. So before we go on, first thing I want to reassure all of you, we're about to deal with differential equations, not from the assumption that you already know what one is, or you already know, or you're expected to have done anything with them. Not at all. With the expectation that you're still getting more and more comfortable with calculus. I know you've had just enough calculus to know what it is and to be expected to get better at it with me and use it in this class. And you've had enough calculus that it is not unfair or unreasonable for us to expect that we could now teach you a little bit of differential equations in this context. We're not here to assume that you, oh, hold on, I'm going to look at I see something in the chat that's cool. I'm going to get to it in 1 second. I just want to make clear, we're not here to assume that you already know differential equations. We're here to assume that you can learn some of them with us in this context, because it would be the next class you would take in a math class if you want to. Okay, so first of all, we're going to learn this together, just like the physicists who had to unpack these things the moment that nature provided these things to them. Okay, nature provides us with a lot of differential equations. Here's the first one we see in nature. We're going to start unpacking it now together and learning something about them as a group. But again, and it's very worthwhile, I think, and it's mostly doable if you go with the assumption that that's what we're doing, not that we already assume it, but that we're doing it together. Now, wait, okay, but I think you get that. So why did, oh, great question in the chat. Bear with me for one. I'm not going to say the person's name because it's direct up, but I'm going to say the, oh, sorry, because it's Thursday, I'm getting, you know what I'm saying. Okay. There's a question in the chat. Why is the X not in the parentheses with the K? Okay, that is a great question. And it's going to push me to the next point I was just about to make. Why I didn't put the X in the K, in the parentheses. I mean, partly that's like a taste thing. Like what physicists tend to do when they're setting up equations, they tend to try to isolate all the constants and put them together at the beginning of an expression, including the constant -1. So they'll put like negative K, and they put all the, physicists tend to put all the constants at the beginning and then try to have the variable sort of separated, or, separated and sort of prominent on its own. So like the simple answer to the question, why is the X not in the parentheses? The simple answer is because X is a variable and I want to focus on it. And particularly it is the dependent variable that's being referred to on the left side with that derivative. Okay, so the simple answer is because X is a variable and it's driving this whole equation. But the even better answer, why I really love this question, and the person should tell me when we're done if I've answered it or not, because that X right there, I'm going to rewrite it, is what makes this a differential equation. All the power is in that X right there. Let me show you what I mean. Okay. The first thing I want to make clear is if we had something like this equation I just wrote here, which we don't, this is like a counterfactual or like a counter example or whatever, like a contrast example. If nature, or if you were just walking down the street, or if you were in a math class and someone just wrote like d2x dt squared equals negative constant times t, okay, that might be intimidating, might be, because it's an equation with a derivative in it, in fact, a second derivative in it, right? But if someone asked you, if they provided you with that equation and said, can you solve for x as a function of t? If the second derivative of x is this, what is x itself? The truth is you could solve that just by doing derivatives backwards twice, right? I mean, like, do I want to get into and don't be intimidated by the twice. Like, if I literally just do I want, yeah, yeah, I will go one step further. If I had that, so I'm going one step further now to make a point. I'm saying, say you knew that the first derivative of x with respect to t is negative k over m t, if you knew that, right? And someone asked, what is x as a function of t? Well, in fact, this is what, whether you knew it or not, this is what we were doing a lot in physics 203. Like, if you know the first derivative of a function, but you're trying to get the function itself, what do? You just do derivative backwards. You just anti-differentiate, which, as many of you have come to realize, often just means you integrate, right? Specifically, if we had that, we would go like this. I'm doing this very quickly. This is all like a contrasting. We would go like, okay, I would multiply both sides by dt. I would go dx equals negative k over mt times dt. Like, I'd bring the dt to both sides, and then I'd integrate both sides. So the integral of dx is x. I'm doing this quickly because I'm just trying to make a quick point. The integral of dx is x, and the integral of the other side would be negative k over mt squared over 2, like, right? And then there would be like a plus c on each side because it's an indefinite integral. And we'd be done. Like, I'm doing that quickly to say, in effect, that's what happened a lot in physics 203. You would know the velocity of something with respect to time, or even better, or if we knew the acceleration with respect to time, if we knew that gravity was pulling you down at 9.8 meters per second every second, then in effect, we could just integrate acceleration once and get velocity. Then we could integrate velocity once and get position. And we would get things like x equals 1 FA t squared plus v naught t, right? Back in physics 203. What I'm saying right now, before I get too far from the point, is if you know a derivative if you have a derivative expressed as a function of the independent variable, then to get the original function, all you do is do the derivatives backwards. You just integrate, right? This right here is an equation with a derivative in it, but it's not a differential equation in any meaningful sense. It's an equation with a derivative in it because it's expressing a derivative as a function of an independent variable, right? Same thing, even here. This one's a little bit more intimidating because it's a second derivative, but even here is expressing the derivative as a function of the independent variable. Whenever you have that, it may be intimidating, but it's actually not a big deal. You just do derivatives backwards to get the original function. And again, whether we knew it or not, that's what we were doing all last semester. But here, here what we have is something far more interesting. Honestly, I mean, it's harder, but it's more interesting. What we have here is a situation where we're saying the rate of change of effect with respect to cause, right? Like the rate of change of x with respect to t is a function not of t, but of x. In other words, we're saying in English, so I'm talking a lot, but this is like the point. Again, I'm going to ask in a second, the person who asked in the direct chat, the person who asked, why is the x not in parentheses? My larger answer to, and it's a great question, and I hope they submit for points, but my larger answer is because the very issue here that we're trying to highlight and focus our attention on is that the derivative of x with respect to t depends on X itself. The fact that the derivative is a function of the dependent variable is literally what makes this thing known as a differential equation. So first of all, so that doesn't mean I've solved it. That just means I'm trying to identify what we're looking at here. So I'm gonna ask again, just if that person could just let me know. I mean, I know I said a lot, but did my okay, great, thank you. I very much appreciate it, because I know I do that, and then by the time that everybody wants to go leave the room, by the time I ever land the plane, anyway. So thank you. Okay, so what am I saying right now to everybody? To get back to the thing, I'm saying okay. So what I'm saying now is what and why it's taken like 5 weeks for us to build to this, like why this is like not a joke. It's totally doable. We're all going to do it. But it's not a joke. We're looking at an equation for which the rate of change, or in this case, the rate of change of the rate of change, but some rate at which the effect changes doesn't depend on the cause. It depends on the effect itself. That's what we're saying. If you think that sounded at all circular, what I just said, you are right. In fact, this is known. So I'll put it in English. In English, what I'm saying is, generally speaking in physics, if you want to know where something is, up until this point, if someone says, hey, where is the thing at a certain moment in time? We would say, well, I don't know, but if you tell me the acceleration, I can tell you, right? Up until now, acceleration is the way that we predict positions. Right, like all that, like how far is the thing fallen? Oh, well, it's the acceleration due to gravity is 9.8. So in 2 seconds, it's fallen 3 meters, or like whatever, right? So in physics, up until this point, if someone asks, what's the position at a given moment in time? We say, well, tell me the acceleration, right? And I'm not taking that back. That's true. But now here, this thing says, what's the position at a certain moment in time? Oh, well, I need to know the acceleration. What's the acceleration? And the answer is, it depends on the position. That's what we're saying, right? We are literally saying the rate of change of position with respect to time actually doesn't depend on time. It depends on the position itself. So it sounds like a circle. And what it's actually known, this type of phenomenon where the rate of change of effect doesn't depend on cause, but depends on effect itself. And again, if your brain bumps at all when I say that, good, you're with me. It should. Like, I'm not saying it's not solvable. I'm saying the amazing thing of math and physics is that such a thing could be solvable. Like, it should. At first, it's like, what? What? So if you're going, what? You're with me. But I'm not, because I just lost myself. What the heck was I about to say? Oh, what this is known as in physics and math, this type of like cause causes effect, and then effect loops back and causes the cause, like this type of the output becomes the input, which is what I'm saying. You know what that's called? It's called feedback. That's literally what feedback is. This is a feedback phenomenon. The position is feeding back into the rate of change of position to affect the new position. And you know, the classic example of feedback is when you put a speaker next to a microphone and the output from the speaker then goes into the input of the microphone, but then that comes out of the speaker. So if you do that, if you bring the microphone too close to the speaker, it like blows it, right? You get an exponential fun. Well, we don't have to get into that at the moment, but this is what feedback is. All differential equations. Differential equations are the mathematical way of expressing some kind of feedback phenomenon where cause leads to effect, but effect leads to cause. Okay, sorry. Oh, okay. Chat. Good, because I should shut up. Is it dependent on the position? Because great question. So, and I guess everybody can see it. So so good call. Katie's asking, because I keep saying, and it's true, I keep saying like the acceleration is dependent on the position, which is the new fact, right? Like that was with gravity, it's not true, right? Acceleration is not dependent on position. It's 9.8, whether you're here or you're here or you're here. Here, acceleration is dependent on position, and Katie's asking why. You know what the answer is? The answer is because of the way springs work, because springs exert a force which is dependent on position, right? And I'm glad she just asked because, yeah, this whole sheet is just based on this seemingly simple equation, F equals negative x, negative kx. It is simple, the equation, but it's not easy. It's simple because it's a linear equation, but the linearity is, if force is dependent on position, that means acceleration, like F equals ma, right? So what that immediately means, I'm just rewriting what we've already done. This thing that's really simple, elasticity, is actually a fascinating phenomenon because the simple thing of a force which gets stronger and stronger as you get farther and farther out from equilibrium means that the rate at which you race back to equilibrium actually depends on where you are from equilibrium. So in short, I'm saying, I'm agreeing with Katie. So she proposed that has to do with the work. I'm not disagreeing with her proposal, but I guess I'm saying it's even more fundamental than that. The work depended on the force. The force is what's funny here. What makes a spring different from gravity is that the force of gravity is just mg. It's constant. Now, remember, that led to enough interesting things. It's like all of physics 203 is dependent on what do we do with constant forces. And that's like a lot of work right there. But now we're at this higher level where the force isn't constant anymore. The force changes depending on where you are. And then suddenly we have a differential equation. Right? Hopefully I answered Katie's question. Maybe she could say or not if I did. But so what we're unpacking here is all the implications that come out when you suddenly say F equals negative kx. Cool. Thank you, Katie. All right, awesome. Right? So I have to keep going. So now I have a differential equation that I have to somehow unpack, that I have to solve. What does it mean to solve? It means I have to somehow do something with it that'll get x as a function of t. And apparently, as though integration weren't hard enough for some of us, what I'm saying right now is we can't even just integrate it. Even if you do like integration, that won't work because it's not a t that's on the right side. It's an x. So I can't even literally I don't even know what I would integrate. Okay. So what do we do? So what do? I do what the physicists did when they originally saw this. Like, again, they didn't already have a math class called differential equations. The math was developed in order to deal with this physics that just came out. I should also, sorry. So I'm trying to teach, right? So I'm saying a lot. This all came out because we're in the middle of step 4 of solving this problem. Of course, please understand, I'm not saying you have to write all of this. If you were in step 4 doing your homework or writing exam, a lot of what I'm saying now, I'm getting myself, I'm like teaching, right? So I leave it to your judgment. When in doubt, on the first time you solve a problem like this in a homework or an exam, the more you can write, the more you're discovering right then for the first time, the better. But then once it's the second time you're solving the problem or the third, you don't have to keep writing all of this stuff. So technically, I'm still in step 4 is what I'm saying. But obviously, you could be a little bit more concise than I can. But so back to step 4, the goal is to solve D2, and to solve means for some x as a function of t. I'm going to keep writing that because it's counterintuitive at first. This is sort of reverse engineering we're doing here. It's a new, like, we're going backwards. We're not using an equation x equals f equal to, like put another way, this differential equation that we just got now has to be solved. That doesn't mean we plug in numbers and get a new number. It means we have to do something with it so that we get an equation that allows us to plug in numbers, okay? So how can we do that? Okay, I'm telling you now, again, this is not, we're going to solve this as scientists, as physicists. Partly because we don't have any other way, just like the original physicists didn't have any other way to solve it. But second of all, because honestly, even in a math class with a differential equation of this nature, this is even what we would do in a math class. Like there, it's not what I mean by being scientific about this. We're going to do two things. Okay, so somewhat quick, and I'm looking. So we got 21 minutes. We're going to guess and check to do this. Now, the honest truth is, with some differential equations that are like easier than this, like some differential equations that you would use, that you would look at the beginning of a math class, like first order differential equations that only have first derivatives in it. Sometimes there's more straightforward ways to solve differential equations. But by the time they get to the second order, like this one is, no matter who you are, the way to solve it is you guess and check. Like no matter who you are, that's what people do. They conjecture and verify. And then, of course, once they get a solution to this, once we get a solution to this differential equation, well, then it'll be true for all time. So anytime we run into this differential equation again, we'll just use that solution again. But this is like, we're getting into real math and science now, where there isn't a straightforward way or a straightforward. So what I'm saying is, as many of you might have gotten used to so far, with differentiating, with taking derivatives, once you get used to it, there's always a straightforward procedure, an algorithm, like do the power rule or do the chain rule or whatever. But you may have noticed that with integration, it's not always that way. With integration is more like puzzle solving and techniques that you build up. And some techniques work for some things and not for others. And you have to sort of get used to it. And it's not always a clear, and many integrals aren't, there isn't even a solution to them, right? Integration is more difficult than differentiation for exactly that reason, that it does not proceed forward. It doesn't seem like traditional math where you just, if you know what to do, you just do it. There's puzzle solving and integration. Well, same thing here. With differential equation, it's puzzle solving. It's guess and check. It's experiment and see if it works. But luckily, two things. One, with differential equations, once we have some kind of good guess, why this really is strict math in the end is that once we have a guess, we can always find out whether the guess is right or wrong. You'll see why in a minute, but because the differential equation we're trying to solve for some kind of x such that if I take two derivatives of x, I get back x itself times a constant times -1. So even if I don't know at first what the answer is, once I think I have a possible answer, I can find out if I'm right by taking two derivatives. That's what we're going to do. You might have noticed that that's what homework 2 is all about. It all looks crazy at first. Homework 2, math methods, it looks out of nowhere at first until you finish homework 1 or we finish. And then you start seeing that homework 2 is a lot of practice of what I'm about to say here. So if you're already intimidated by it or you haven't finished it or you haven't even started it, there's still time to look at it with fresh eyes from all this. Number 2, where do we even get our conjectures from? Where are we even going to get, how am I going to know what to guess for the, because I've been spending time in the lab, because this is coming from the physical world. So the physical world will motivate my conjectures and then I will mathematically test them to see if they're right. So here's what I mean. So here we go. So this is all still step 4, for good or for bad. Obviously, those two things in English that I just wrote, you wouldn't have to write in your homework, but okay. If you've ever played with springs and masses in the lab, which you totally have, or if you've ever played with systems that are oscillating back and forth in any kind of reliable way in the lab, which you have, like you moved on to pendulums and stuff, right? You've been looking at a lot of oscillating systems in the lab. So one thing you've either seen explicitly or you, I think, could believe from having been in the lab is that if there, remember, I'm looking for x as a function of t. I'm looking for where this thing is at any given moment in time. So let me picture in my mind, if I let something go back and forth in time in the lab, and I was charting like where is the mass at every single second. If I in the lab, I would make a graph of that data that I collected. And if I could recognize the shape of the graph, that would tell me a lot about the type of function it is, right? In other words, to try to come up with a function is to try to come up with a graph in a way. Now, I believe that you believe that if we did this enough in the lab, if we tracked a mass going back and forth along the x-axis or the y-axis, whatever, in time, the mass would start someplace called x naught, right? It didn't, we started it at some place that wasn't 0. If we start at 0, it's not going to go anywhere. But if we hold it at some initial position x naught and let it go, the mass starts coming into equilibrium, gets to equilibrium, keeps going, gets to a turning point on the equal side on the other side, the equal displacement on the other side, and then turns around and keep, right? Like, you know. And you know from all of our answers in questions 1 through 8 that if we were to think about what this position is doing as a function of time, the smoothest possible, simplest possible shape or pattern of this motion would look like that. And you know that what that is some kind of cosine graph, right? I'm specific, right? I'm just to cut to the chase. If you just think about your experience in lab. Now, by the way, I know you've done various graphs and various different explorations in lab. And I do know, for example, the very first exploration you did in lab 1, you were graphing period as a function of mass and other things like that. I understand that. You've done many graphs, but so they've all had different shapes. But right now, what we're interested in is x as a like x measured in meters as a function of time measured in seconds. Like that's our issue here. We're looking, again, for x as a function of t. So that graph would look like this. I think if you even just look at our answers for questions 1 through 8, you would agree. Now I'm calling this a cosine. I think this is recognizable as a cosine graph. Notice I'm saying cosine, not sine. It is in effect also, but I mean, cosine and sine are very similar, but they're just like shifted from each other by, they're all out of phase with each other by pi over 2 radians or whatever you want to say. So why am I saying cosine? Because this one is not starting at the origin, right? If I start the mass at 0, 0, it doesn't go anywhere. The whole assumption is that I started it at off 0. So I believe cosine is the best description in general of what we're talking about here. So have I solved all my problems? No, but I've now made another huge leap of progress. What I believe for my conjecture. I'm trying to build a conjecture from my lab experience or from my mental memory of lab experience. So I believe so far, my working conjecture is that X is some kind of cosine function of T. If I'm going to be careful and I have a little bit of experience, so I'm going to say X is some kind of cosine of T, but I'm saying some kind because I have a little experience in this area. And I'm leaving a little room for the fact that, yeah, I believe that that cosine is the right way to go here, but I don't believe it's so simple and so direct as just X equals cosine of T. I believe I better leave some room for the fact that T might be multiplied by something and the cosine might be multiplied by something. Now, why would I know to do that? Like, how do I know to do that? Well, yes, from experience, but more specifically, because I'm being a scientist, not just a mathematician. And what I believe, I'm leaving blanks because I'm picturing the lab and I'm picturing that these are measurements. And I believe that measurements in science are always accompanied by units, right? And units are very important in science. I believe that the units of time are seconds. And I don't believe you can take the cosine of a second, right? You could take the cosines of angles that are measured in degrees or far better radians, and we're going to have to deal with radians a lot in this class. We'll unpack them too. But whatever, you take the cosine of an angle, you don't take the cosine of a second. So, and similarly, when you take a cosine of something like pi over 2 radians, you get a number. You don't get a number of kilograms or a number of seconds or a number of meters. You just get a pure number. So we're supposed to be plugging in some kind of seconds and spitting out some kind of meters. For that to happen, there's got to be more going on than just the cosine. So, and I'm watching the clock. Obviously, stop me if I'm not. I mean, I know I'm whatever. Just stop me if and when I'm not making sense. But my work, and remember, I'm trying to build up a conjecture here, just a conjecture. Just saying that I have a conjecture doesn't make it mathematically or scientifically correct, but I'm trying to get to the point where I have a conjecture that's good enough or plausible enough, convincing enough that then I can test it to see whether it's exactly right or not. And that's what I'm going to do. That's the goal. So what I'm saying is so far, my working conjecture is X equals something times cosine of something times T. And the somethings are dictated by units. So let's go one at a time. This thing here. And those somethings, sorry, whatever those somethings are, some kind of numbers or something that's going to go in there, but they're not variables. They're not variables because it's two and only two variables in this whole expression are already taken care of. T is the independent variable, X is the dependent variable. So whatever is going to go in those blanks are some kind of constants. Okay, so some constant is going to go in that blank. I don't know anything about it yet, other than it has to be measured in radians per second, so that the seconds cancel with the seconds of time and you're left with just radians. And then I can take a cosine of that, right? And then you take the cosine of something measured in radians, and what that spits out is a pure number. So then that pure number must be multiplied by something that is measured in meters in order for this whole answer to be right. Like that much I know from science already. So each of these is, that's all I know so far, is that there must be a constant in each of these blanks, and each constant has to have a certain kind of units. So now I'm going to give a name to those constants. I'm just going to give a name to hold their place in the thing. It doesn't mean I have any, well, whatever. I'm just going to give a name to each one. So I'm going to let this, I'm going to let it be called lowercase omega. Obviously, that's with the benefit of hindsight because everybody else calls it that. You could call it whatever. But it turns out that what we tend to call it is omega. And all I know about it right now is that whatever omega is It's measured in radians per second, which means it's some kind of rate, right? In fact, I don't want to get back. In fact, as you may know from lab, well, let me say, it's some kind of rate. It's the rate at which something is advancing through radians, not through space, through radians. So it's the rate at which something somehow is sweeping through angles of some kind. So people call this thing the angular frequency. That may or may not, I don't know if that's helpful or intimidating. I'm going to unpack it more next class than this class. But all I know right now is that there's some constant rate at which radians per second are being traversed, and I'm going to call that rate omega. Similarly, this thing, so I'm going to put it in. Similarly, this thing over here, this I know a little bit more about already. It's got to be some kind of position or displacement measured in meters. And the fact is, I actually know what it is because cosine itself just ranges from -1 to 1, right? Like a pure cosine graph does that. It ranges from -1 to 1. We know that this mass, and just the numbers, -1 and 1. We know the mass on our spring is ranging, in this case, back and forth between like 0.15 meters and -0.15 meters, right? In other words, bottom line, what's got to go in here is what we've been calling x naught, or the initial position of the mass. Why? Well, first of all, it's measured in meters. But second of all, if you think about it, when t is zero, the cosine of any number times 0 is the cosine of 0. The cosine of 0 is 1. So if we don't put any blank before this whole cosine expression, it implies by itself that literally wherever the thing starts at t equals 0 is the number 1. But we know the thing starts at x naught. So x naught is the value that this whole expression should have when t equals 0. And if I multiply that whole cosine thing by x naught, then now I'll have a cosine graph that doesn't just range back and forth between -1 and 1 unitless. I'll have something that's stretched out that ranges between -0.15 meters and +0.5 meters. So my conjecture right now, I am watching the clock, my conjecture is a complete conjecture now. The working conjecture is that x somehow ranges this way. I don't know anything about the omega really yet, except it's the rate at which this thing goes back and forth through angles of some kind. That's all I know about it. Yeah. So now with 6 minutes left, I'm not claiming to know anything more about the omega, but I do think this is an equation that could solve my original differential equation. Like this could be the answer. I don't know. But if I'm right that it's the answer, and as long as I can find out what omega is and I know what x naught is, then this would be a function where if I plug in 1 second for t, it would spit out x. So if this is right, like we're done with question 9 and we're happy. But how do I know if this is right? I have to test. How do I test? And again, if you look back, once I do this now with 5 minutes left, once I do this now, you'll really see what the heck was going on at the beginning of homework 2. And sorry, what's inside the parentheses? Really good question. What's inside the parentheses is omega times t. Okay, and omega is some constant that we don't know anything about yet, other than it must be measured in radians per second. Okay, great. You're welcome. Thank you for closing the loop. So this is my working hypothesis. No one's claiming that we know what omega is yet, but we believe that this is an equation that could solve our differential equation. How do we test it? This is what the beginning of homework 2 is all about. We take derivatives. How many derivatives? Because we're trying to see whether the second derivative of this spits back this times a constant times a negative sign. So very quickly, so I'm going to test. I'm going to first take a derivative. Now I'm going to do this a little bit quickly because we only have 4 minutes left. You should flag this in your, I'm going to take a derivative of that. And I'm going to do it quickly because we're running out of time. I'm going to tell you right now, it requires knowing trig derivatives. Like you need to know that the derivative of cosine is negative sine. And you need to know the chain rule to do this. I'm going to do the trig derivative, that cosine becomes negative sine, and I'm thinking that this is chain rule. This is cosine of a function. So I've got to do the whole derivative times the derivative of the inside. I'm happy to speak that slower next Monday, honestly, to anybody and everybody who needs it. Make a note if you're uncomfortable with either trig derivatives or chain rule, but that's what I'm using here. So I'm saying, for the moment, I'm saying this, I'm saying the derivative is this, to cut to the chase. Like the first, right? So I'm basically saying it's negative sine of x naught. It's negative x naught sine omega t, but then I'm multiplying the whole thing by an omega because of chain rule. And I'm bringing that omega all the way to the outside because of this physicist habit of we like to isolate all the constants next to each other. And then put the variables at the end. Okay, I'm just watching the clock. So that's, again, please flag if you need more help with that, or get yourself some help this week, whatever. That's the first derivative. Now I got to take a derivative again. Why? Because the differential equation had a second derivative in it. So I'm going to take a derivative again. If I take a derivative again, the derivative of cosine was negative sine. But the derivative of sine is not negative cosine, it's just cosine, right? Like maybe review. So I introduced a negative sign in the last derivative, but it doesn't go, I don't introduce another one now. It doesn't go away now. So I get x naught omega cosine of omega t, but I had to do the chain rule again. So the omega does come out again. So I get omega squared this time. Again, I'm going a little, we got 2 minutes left. So that's the derivative, right? And let me, in fact, rearrange one more. So I get, since multiplication is commutative, I can write it like this. If I just shove that constant all the way to the left side. Now, so what? With 2 minutes left, so what? The so what is this. This whole business right here is what we're conjecturing x to be, right? So what we just established is that if you take two derivatives, if you use that x, that expression for x that we're conjecturing, it turns out if you take two derivatives of it, you do get itself back times some kind of constant, a constant squared is a constant, times -1. So this is looking good. In other words, if x equals x naught cosine omega t, then apparently the second derivative of x with respect to t does equal some constant times -1 times x itself. And we wanted that. We wanted some x such that if we took two derivatives of it, we got back some constant times -1 times itself. So apparently with 1 minute left, what I'm saying, this is a little bit confusing, but I'm saying, oh my God, we did solve. We did figure out a function that when you differentiate it twice, you get back itself times a constant times -1. The only thing is, this is all true and this all worked. This all checks. This works. This works. This solves as long as omega squared, the thing that we didn't even know, or yeah, as long as omega squared, the thing that we didn't know much about except its units, if that's just another name for the constant k over m, if in other words, omega is the square root of k over m, if that's just two different names for the same number, then this works. And they are, or they can be. So as long as this thing oscillates at an angular frequency that is determined by the square root of k over m, then this thing works. In other words, and I know we're at 1:30, I'm just going to, in other words, i.e., the solution to this whole thing is x equals x naught cosine of square root of k over m times t. That's the thing we've been looking for. That's our answer. And if we plug in 0.15 cosine of square root of 200 over 0.3 and plug in the 1 for 1 second, and if our calculator's in radian mode, if we plug in those numbers, we will get an answer, which is 0.116 meters. So bottom line, and I know we're done. I'm putting down the cannoli and the pen. The answer to question 9 is 0.116 meters approximately. But the real answer is that the real answer is, the real answer for all time is x equals x naught cosine omega t if omega is square root of k over m. That solves solves this differential equation for all time. Now we're done. I'm done. You can go. Have a nice day. But oh, good. Thank you. Yes, yes. Awesome, awesome. And anybody who wants to keep asking questions, I'm not going anywhere. Wait, these are great. Yes, Katie, awesome. And that's the way it goes. You always get it first. Wait, should we have to explain what the yes, please do at least the first time. And I will say that again on Monday. But if you're doing homework or an exam, please at least the first time identify trig, thing, and chain rule. And I'll show you how on Monday. But yes, great, great, great. Yes, yes. I'm just looking. But anybody wants to ask more questions, you can. But yes, great. No, that's awesome.
Can you go back to the last slide?
Oh, sorry. Can I what? Can I read this
Go
last
back
line?
to the last slide. The one that had like the cosine with the numbers in it.
Oh, yeah, sorry. This right
Yeah,
here?
that one.
Okay, yeah, sorry. Oh, great. Oh, great, Maria. Okay. Thank you for that. No, I'm glad. And if it good. And it well, okay. And please, I hope you just don't think, well, anyway, good. I'm glad. And it goes like that. I mean, I know it didn't make sense. Anyway, I'll just shut up. I'm glad if it makes sense now. That's good. That's good.
Thank you.
Thank you,
Yeah,
guys.
it definitely makes sense. Don't worry.
Okay, cool. No, and I guess I'm just also, I know if there's a little part in your heart or your brain that's like, oh, you could have said this 3 weeks ago. Like, I know that.
Yeah.
But honestly, from my experience, here's the deal. Really, 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 we could have, and it wouldn't have meant anything. And we've tried it. The real truth is we couldn't have. The reason it makes sense now is because you've been just frustrated and annoyed and thinking about it your way enough that this was the final glue that you needed. I mean, I know I said this at the beginning, but I really mean it. Like, it makes sense now because you know what you've been looking for, so now you've found it. If we give this to you first, you don't even know what it's just literally abstract memorization that doesn't mean any, and then you wouldn't know. For what it's worth.
Yeah, and you know what? It feels so nice knowing that like everyone was like on the right track to like eventually getting it, even if we didn't have this lecture yet.
No, and you good, and yes, and I believe you were, and I know from your, I think you were absolutely no, and I think you guys are, yes, exactly, and that is the thing too, is like the real thing of all this is like really, really, like really doing physics is like we're really trying to show you how the thought process, and you can see it's a very long thought process. We can't expect you just like automatically to know how to do that thought process, but we are trying to show you like eventually when you, especially, well, you know, from your like the conferences you've gone to and stuff, like in the end, like you are this person, just maybe not with this, you know, with whatever material you choose, then you become the person that actually does do the original thought process. So that's it. But yes, no, I'm glad it makes sense. I'm glad.
Yes, thank you so much.
Thank you. Cool. All right. Awesome. Thanks. Okay. And Harrison, are you still there? Do you want to ask a question, or are you just in another room? If you're there, I'm happy to ask a question. I mean, answer a question. And if not, I'm going to shut this party down. Okay, I think I'm shutting the party down. 3, 2, 1. Have a nice day, everyone.